Alright, third video. I'm afraid this is gonna be, I'm afraid the difficulty is just gonna keep ramping up slowly from here on out. If all goes well, third video, then fourth video, and hopefully we'll be done with understanding all that we need to know about Fermat's little theorem. If not, then, oh well, I'll try my best. And you should also try your best to understand things. Number 3, third video, last time we talked about groups. Now we still want to talk about groups because I'm not done talking about it yet. There are 3 facts you should know about groups. Over here, we talked about the characteristics of a group. We talked about, I'm just going to remind you that a group needs to satisfy 4 properties. Maybe I'll write them down again. Number 1 is closure. Number 2 is associativity. Just as a little refresher. Number 3 is identity. Number 4 is inverses. And we took a look at examples of a group. One of them is the regular old number system. We have 0, 1, -1, extend, extend. We also have what we call a cyclic group. This one is finite instead of infinite like this one. We took a look at this example of a finite group that only has 4 elements instead of this thing which has an infinite number. Alright, I'm gonna tell you 3 more facts about groups aside from these 4 characteristics. Number 1, but you only need to check these 4 to check to see if it's a group or not. If it satisfies these 4, it is a group, right? So if it is a group, if all of these 4 are checked, that means that we can identify extra characteristics that make groups special and that make groups worth studying. Why? Because they satisfy 3 facts, like I've said and repeated at least a couple of times now. The 3 facts that we're going to go over today. Number 1, I'm just going to say, you can create the group by using the same element and repeating the binary operation. Is my ink running out? Yeah, my ink is running out. I'm gonna get a new marker real quick. Right, new marker. Brand new, it still has plastic all over it. Voila. Let's just put you here. Right, let's just rewrite this because the color is already fading out. Alright, using the same element and repeating the binary operation. And you can create a group by doing that. Alright, so let's take a look at an example, okay? Let's take a look at this cycle over here. You can create a group by using the same element. That means that we can pick any element that we want. Let's pick 1, for example. Alright? Alright, so we have number 1. Alright, let's use the same element and repeat the binary operation. What is the binary operation here? It's addition, if you still remember from the previous video. So we have 1, and then we have 1 plus 1. And let's keep doing it. We have 1 plus 1 plus 1. And we have 1 plus 1 plus 1 plus 1 4 times, and we can just keep going on and on and on and on. Of course, because this is a finite group, it's going to loop back at some point, just as the structure suggests. So 1 is just 1. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 plus 1, what is that? 1 plus 1 plus 1 plus 1, that's 0. And if we do it 5 times, well, 1 plus 1 plus 1 plus 1 plus 1, that's 5 times. 1, 2, 3, 4. Oh yeah, 5 including like itself. So 1 plus 1 plus 1 plus 1 plus 1. 5 times, we go back to 1. And you see that the whole cycle just repeats again. If we do the next one, we know that it's going to be 2. If we do the next one, we know that it's going to be 3. So we can ignore this repeating segment over here. Right, so if we ignore the repeating segment, we have 1, 2, 3, and 0. What is this? This is our group again, right? Pretty cool. And not only 1 satisfies this property, every single element satisfies that property as well. Right, very cool. Let's try with it with a different number instead. Let's try 3 now. If we have 3 and if we repeat the binary operation as we've said, we keep following the pattern, we're gonna end up with the same result as we did when we used the number 1. 3 is just 3. What is 3 plus 3? 3 plus 3 is 3 plus 1 plus 2 plus 3. 3 plus 3 is 2. 3 plus 3 plus 3, well, that's just 1, right? You can do this calculation yourself. 3 plus 3 plus 3 plus 3 is just same as 1 plus 3, because like 3 plus 3 plus 3 is 1. Alright, so if we add another 3 to it, it's same as adding 1 with 3. So when we add 1 with 3, that comes back to 0. So we got the same thing as 1. What is 3, 2, 1, and 0? We got our group back again. Pretty cool, right? So not only 1 has that special property, every single element in the group, no matter what you pick, has that same property. Now, but how does it work with 0? Because 0 adds with itself, and you're just going to keep getting 0 all over again, right? We have 0, we have 0 plus 0, we have 0 plus 0 plus 0. Well, it doesn't matter now, because we know that the answer there is all going to be 0. We get rid of the repeating parts, which means that everything we end up over here is just 0. You can create a group by using the same element and repeating the binary operation. What have we just created when we did this? We created a group. 0 is a group. Apparently. Well, let's check the facts of closure, associativity, identity, and inverse. Alright? So closure says that if we add 2 elements together from the group, we're going to get another element of the group. So there's only one element here. So what's 0 plus 0? 0 plus 0 is 0, right? And 0 is still within the same group. So when you add 0 plus 0, that equals to 0. This is part of the group. This is also part of the group. Cool. Associativity, we're using addition here, so definitely it is associative. What is the identity? The identity is 0, and 0 exists inside the group. What is the inverse? Inverse, if you pick any element of the group 0, that means that there must exist an inverse element. And what's the property of inverses? When you add an element with its inverse, you're going to get the identity back again. Does this number exist? And is it located within the group? Sure, A inverse is 0, and 0 is located within the group. So this is a group. Therefore, this thing checks out. Pretty cool, right? So 0 itself, the one element group. So we've seen a cycle group now. Now we can add it to the list of examples. Just plain old 0 itself. this also forms a group as well. Now let's try it with this. Let's try repeating 2 with addition and see what kind of group we get, because that's a different group this time. Alright, so let's start with 2. Next we'll have 2 plus 2. Next we'll have 2 plus 2 plus 2, and so on. What's 2? 2 is 2. What's 2 plus 2? That is 0, right? According to this cycle thing here. What's 2 plus 2 plus 2? 2 plus 2 plus 2. We go back to 2. And if we keep going on, we're going to get 0 and 2 and 0 and 2 again. What do? We get rid of the repeating parts, because it doesn't matter. And apparently, this thing here forms a group. 2 and 0 forms a group. We can go and check again. What's 0 plus 0? That's 0. What's 0 plus 2? That's 2. What's 2 plus 2? That's 0. Any single combination. This is every single combination of the group, right? 2 and 0, 0 and 0, and 2 and 2. Every single possible addition that you make, you're always going to end up with an element that is within the group here. Therefore, closure is satisfied. No matter what you add, you're definitely going to get something that is part of the group still. Associativity, we're using addition, so that's check. Identity, we have 0, so that's check. What is the inverse of 0? The inverse of 0, as we have seen, is 0. What is the inverse of 2? The inverse of 2 is apparently 2, because you add 2 with itself to get 0. So the inverse does exist, because 2 exists within the group. And this also forms a group. Pretty cool, right? So that's the first statement. We can always create a group by picking one element and repeating the same binary operation over and over and over again until it loops back and repeats. For the case of this big number system here, we're never going to loop back, okay? If we have 1, we have 1 plus 1, we have 1 plus 1 plus 1, we have 1, 2, 3, then 4, then 5, then 6. We're just going to end up extending the line when we repeat 1. And we also have to do it backwards as well. -1, -2, -3, -4. Because over here, we only need to generate it with 1 and 1 and 1 and 1 and 1, because it can loop back around. Over here, if we generate it with 1, it's going to keep extending forward and forward and forward again. And it's never going to loop backwards because of its infinite size. Over here we have a finite size, therefore we only need to generate it one way to get the entire group. Over here we have to generate it both ways to get the entire group. I hope you can understand or get the logic behind that. That's why this thing is only true for finite groups, because it's finite, you can loop back at some point. If it's infinite, you have to generate it in both directions. Therefore, you can create the group by using 2 elements if it's an infinite group, and you can create it with 1 element with a finite group, because you can loop back around, and 2 elements here because you have to extend one way and you have to extend the other way. So that's what repeating the binary operation does. It basically extends, you go from 1, then to 2, and then to 3, and then to 0. That's why you can create a group, because you're going around the group and you're selecting elements from it. Sometimes you only select 2 and 0, but that works out as well. Sometimes you select the whole group, that works as well. Sometimes you select 0 only. You're going around the group by adding 0 and 0 and 0 and 0, but you're staying stuck at one place. And that also forms a group as well. I hope I'm not going too quickly. But yeah, the point is pretty easy to make. Next thing. When we create a group in this way, we're going to get a set of elements, right? We're going to get an element A. we're going to get a plus a, so I'm just going to write that as 2a. We're going to get a plus a plus a, so we're just going to write that as 3a. That's the same thing. 4a, something, 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 and we're going to get back to a again. This is special for finite groups only, because as we've said, infinite groups, they don't loop back around because of its property that it extends to infinity. So you're never going to loop back around. So this is only for finite groups. And for our proof of Fermat's theorem, we're going to be using finite groups to prove it. So just concentrate your mind power onto finite groups instead. But it is helpful to identify differences just so you can get that extra understanding. So this is only available for finite groups. It loops back around. What I'm saying is the last element here, the last element, whatever that is going to be the identity, always the identity. The element before the repeating segment is always going to be the identity. Alright, so cool, right? So we have a, 2a, 3a, 4a, and we have some number times a, for example, right? We don't know what this number is because we don't know how long it will repeat by. It depends on the size of the group. If it's like this, that means that it's going to repeat every 4 turns because the group is size 4. If it's a much bigger circle, then it's going to repeat like every 10 times or something. So it depends on the group. So we have a number here, BA, to represent at which point is it going to repeat itself. Now we also notice that B is the size of the group. Why? Well, because remember, we have to cut off the repeating segment, right? So we have to cut off the A, and everything here forms a group. B is the size of the group, because how many elements do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 blah. We have B, BA elements. So we have B as the size of the group. And what did we say? B is the size of the group, and A times B is equal to the identity. Pretty cool, right? So that is if you repeatedly but this notation here, A and A plus A and A plus A plus A and A plus A plus A plus A plus A, what binary operation are we using there? We're using addition as the binary operation. So what is the identity for addition? That identity is 0. AB is 0, where B is the size of the group. And this is our second point. Let's see that in action. So I'm going to erase the first part here. Hopefully you remember the first part already. And let's try to generate a group with the first rule. Alright? We're going to create a new group with the first rule, and we're going to see if this statement holds. So let's use 2, okay? So we have 2, and we have 2 plus 2, which is 0. And we have 2 plus 2 plus 2, which is 2 again. And apparently we have a repeating segment over here, so we can get rid of that. And 2, 0 is our new group, right? What's the size of the group? The size of the group is 2, alright? 2 is the size of the group, so B is 2. What's A? A is the element we use to generate the group, right? A is 2. That means that 2 times 2. 2 times 2 is same as 2 added with 2. Yeah, that's the same thing. 2 times 2 is equal to 0, therefore 2 plus 2 is equal to 0. That's what this rule says. 2 plus 2 is equal to 0. Is this true? 2 plus 2 is equal to 0. Yeah, it appears to be true. Cool. Let's try to generate a different group. Let's try to generate a group with 3 now. We have 3. We have 3 plus 3. 3 plus 3 is 1, 2, 3. 3 plus 3 is 2. 2 plus 3 is 1, 2, 3. 2 plus 3 is 1. 1 plus 3 is 1 plus 1 plus 1 plus 1 is 0. And again, remember, the last element here is always going to be E, the identity, or 0. Cool, right? This statement always works. And what do we have? What's the size of the group? 4. Okay, cool, right? 4 is the size. B is the size. 4 is the size. What did we use to generate the group with? We used 3. Therefore, 4 times 3 is going to be 0. Cool. So 4 times 3 is 12. So basically, we go around the circle 12 times. Oh, I'm not looking forward to this. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, we got 0. See, this rule always works. See, groups are fun. They follow these amazing rules. Last element of the group that we generate with the first rule is always gonna have 0, or it's gonna always have the identity whenever it is at the last place. You may want to ask why this is true. Well, if we were to extend this forward again, what will we get? Right? We'll get BA plus A. And we said that this is the last element. This is the last element, right? That means that the next one will be repeating again. That means BA plus A is A. Alright. BA does nothing to A, right? As you can see, A remains unchanged. BA does nothing to A. So what is BA? BA is the element. Right, so that's the intuitive reason of why the identity is always at the last place, because it follows that logic here. So that's the second rule. And now we reach to our third rule. And once we have all of these rules, we're going to use all of them in order to prove Fermat's little theorem. And we just need one more component to figure that out. 3. 3 states that the group is equal to a subgroup. I will define what a subgroup means later on. Union. I hope you know what union means also. I think you should have studied it some time ago. A group can be created, not created. A group is equivalent to a subgroup union the subgroup plus 1, union the subgroup plus 2, union the subgroup plus 3, where 1, 2, and 3 are elements of the group. And of course we have union subgroup plus 0. I don't know if you can see it at the edge there. So we have the subgroup itself, and then we have the subgroup plus each and every element here. So if we have an infinite set, like the top part here, we're going to have the subgroup union subgroup plus 1 all the way till subgroup plus 100 or subgroup plus 5,633 or something like that. It's going to keep going on forever. Luckily, we're only dealing with finite groups over here. That's why we only, this formula here, it stops at some point, because you're going to go over every single group, because it's a finite limited number, unlike the top part here. So luckily, we'll be dealing with a simpler formula. Cool. So what does a subgroup mean? Well, we know what a group is, right? That's simple enough. What's a subgroup? A subgroup is a group that is smaller than the initial group. So what we've seen before, we've seen that 0 is a group, right? And I think we have 2, 0 here. We've also seen that that was a group. These are subgroups of this bigger group, because these are smaller groups. They only have 2 elements, but they are located within this bigger group, which has 4 elements. So that's what a subgroup is. Pretty easy to understand. Union, I'll just talk about it a bit. Let's say we have a set of numbers 1, 2, and 3, and we union it with 2, 3, and 4. What's the answer to this? Well, I hope like this type of question has jogged up your memory a bit. the answer is 1, 2, 3, and 4. It doesn't matter if we have duplicates, we can get rid of it. So it's same like the previous example, just get rid of the duplicates. And this is our new set of elements. So number 3 states that this is always true. So let's take a look at an example. So what is our group in this case? Our group is 0, 1, 2, and 3. So we have 0, 1, 2, and 3. Cool. Is equal to a subgroup. We can pick any one of these. Let's pick 2, 0. 2, 0 union with subgroup plus 1. What do I mean by subgroup plus 1? The subgroup we're dealing with is 2, 0. Plus 1 means you add 1 individually to each of these. That's going to make it 3 and 1, right? 3 and 1. Cool. Let's union it with subgroup plus 2. So we have 2 plus 2, which is 0. We have 0 plus 2, which is 2. We have union subgroup plus 3. 2 plus 3 is 1. 0 plus 3 is 3. We have union again, subgroup plus 0. Subgroup plus 0 is just the same thing itself because we know that 0 is the identity, which means it does absolutely nothing. So we can just repeat 2, 0 again. So what happens when you take the union of all of these elements? What is the union here? Well, we can get rid of duplicates. 0 is already included, 2 is already included, 1 is already included, 3 is already included. So what's the union of 2, 0, and 3 and 1? You combine these two things together, you get 2, 0, 1, 3. Which is exactly the same as the original set of groups that we're dealing with. Cool. So what does this mean? Why is this formula important? Well, what is the size of the subgroup? Well, the size of the subgroup has got to be less than the group, right? So if the group has B is the size of the group, that means SG is a number less than B, right? So let's just say A, where A is less than B. A is less than B. Alright, cool. And apparently B is equal to A union subgroup plus 1, subgroup plus 2, subgroup plus 3, subgroup plus 0. What is the size of this group, right? If this subgroup has the size of 2, which means it has like 2 and 0 inside of it, that's just an example of a subgroup with a size of 2. What's the size of subgroup plus 1? Well, you add 1 here and you add 1 here, you end up with 3 and you end up with 1. Well, that doesn't change the size of the group at all, right? So if we have like a subgroup with 3 elements, for example, like 0, 1, 2, 3, or 0, 1, 2, for example. So this is a 3-size subgroup, and we add 1 to it. So basically this turns into 1, this turns into 2, this turns into 3. This is subgroup plus 1 in the case where the size is 3. That means that this is subgroup plus 1. And what's the size of this? 3. Adding to a subgroup doesn't change the size at all. Cool, right? So basically A is union with A plus 1, union with A plus 2, blah, 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 blah. What is the size of A? The size of A is A. What's the size of A plus 1? The size of A plus 1 is A. The size of A plus 2 is also A. So A is the size of the group, right? And it doesn't matter if we add it like by 1 or by 2 or by 3. A is still going to be the size of the group. So we have a group here of size A, and we're going to combine it with another group. This is a different group, right? Subgroup and subgroup plus 1. These two are different groups. So A combines with a different subgroup, but with the same size. So what size is this going to be? The size of this group is going to be 2A, right? Because you combine a group of size A. Let's say A is 2, okay? A is 2. A group of size 2, and you combine it with a different group. It has to be a different group of size 2 as well. What are you going to get? You're going to get group of size 4 because you just add 2 with 2. So if you have a group of size A and you combine it with another group of size A, you're going to get a group that has the size of 2A, depending on what A is. Alright, we keep going on and on and on. A, union A, union A, union A. All of these groups have the same size. We're going to get some multiple of A. We're dealing with a finite group, so it has to end at some point. So we have KA, where K is any number depending on how many times you have to repeatedly add the elements together. Right, so B is equal to KA, where I'm going to remind you what B is again. B is the size of the group. What is A? A is the size of the subgroup. Cool. So what does this mean? It means that the size of the group is always a multiple of the size of the subgroup. Cool. Size of the group is always the multiple of the size of the subgroup. Right, so if we have a subgroup of 3, if our subgroup is 3, has a size of 3, that means our group must be a multiple of 3. Our original group that contains the subgroup, like, I don't know, just imagine these are hands. This group contains the subgroup. What size must this group be? It must be a multiple, because we have this rule here that says that it should be a multiple, right? Just like we've shown and proven before. So this group here, what could it be? It could be any multiple of 3. It could be 6, it could be 9, it could be 12, but it can't be 5. A group of order 5, order is the size, by the way. So if a group has a size of 5, that means it's impossible for it to have a subgroup that has a size of 3. Right, so that's it, basically. So these are the 3 rules that groups have to follow. So you use these 4 rules to identify what a group is. Once you have identified that this thing is a group, then you know that it follows these 3 properties. That number 1, you can create a group by picking an element from it, and you can repeatedly use the same binary operation again. Number 2, the last element that you generate from rule number 1 is always going to be the identity element. Number 3, size of the group is always a multiple of the size of the subgroup. Cool, so these are the 3 rules that groups follow once you have identified that it is properly a group. And we will use these 3 rules and what we have learned in the very first video in order to prove Fermat's little theorem. Okay, that's it. Bye.